Then I have to open parentheses or put a dash here. They actually call it formally the second part. Okay. And then later on, I'm going to explain why it's called the second part. It's more like a historical development of that theorem. But now these days, this part right here that we learn is a lot more useful for me, so we learn it fast. All right. So let's not worry about what the fundamental theorem of calculus is yet. Let's look back at that problem that we've done. So, and you guys start trying some of the homework with the definite intervals, and you got to go through the limits thing like that, and it start getting tedious, right?
Yes.
So you can see that it's tedious, but that's how it was done. That's how it's supposed to be done historically before this theorem came out. Okay, so it was just getting this integral, right, to represent an area. See what I'm saying? Notice that's surprisingly the simple look, right? Simple look. And then it took us so much work. Go through the Riemann sum, take the limit to infinity. You guys have seen that from the last lecture, right? Just to get to the answer 1/3 here. And that at 1/3, I mean a precise answer. And then, so think of that. See, importantly, you can think of that. You can interpret that as an area, right? From 0 to 1 underneath the curve of x squared function here, right? Between 0 to 1. That's the integration interval with that. Okay? But then think about the mathematicians who were coming up with this. As they crank through that limit process long enough, right? They start thinking to themselves, well, really, do we have to do this every single time? Because there are a lot of functions out there. See what I'm saying? There are a lot of functions out there. And you see the one secret ingredient behind the scene for all of these summation is we got to rely on the summation of I, right, to turn into a general expression. And that was 1 over the 2, right? And then the summation of I squared, right? I showed you in class right there. And then that runs into an n times n plus 1, and then the 2n plus 1 over 6, right? For I running from 1 to n, whatever, right? But what about a summation when it's like an e to the I? We got functions at e to the x, but what about the summation for e to the i's? Nobody knows these days, right? So it was such a challenge for mathematicians back then, because these are only particularly good when our function was at polynomials with the powers and all that, right? But when it comes to beyond these things right here, then we're really hand-tied. See what I'm saying? No? And so, obviously, using the summation and go through the limits, at some point we gotta find a way to break over that. We gotta find a way to overcome with that, right? And so now here's how the fundamentals calculus right here. And I'm just writing down a sketchy version on the board right here, and then you can find that all over your textbook. Because textbook will always have the best precise worded the description of the theorem right here. But they call it the second part. So I'm going to say that f of x, right, be a continuous function. Or how about a function continuous function? Is continuous over some interval. That's the idea here. Outside of that interval, whether it's continuous or not, that's not important. But at least in the interval from a to b here, if we know it's continuous, right? The definite integral of the function f of x with respect to x, accumulating everything from a to b. Okay, that's right here. The way to calculate that is equal to the capital F of b, or more precisely speaking, right here. We introduce that symbol, capital F, and evaluate it from a to b. But that really means you take the capital F, substituting b into it, and capital F, substituting a into that. What exactly is capital F? Capital F is some function that's satisfying f prime equal to lowercase f. Yeah. Right. And so I just tend to write down the sketchy version of the theorem where it's focused on the highlighted information. So go ahead and spend some time writing it down. This is the idea. You see, you got to understand, before this thing is born, right? A theorem, by the way, a theorem in math is a truth that was proven, and now once it's proven, right, it's a truth that you can start using it. See what I'm saying? Huh? So a little bit of history. historically here, but Isaac Newton came up with this. That famous physicist, and he's also the one, because of physics work, okay, this thing came out. You know what I'm saying? No? But anyway, so credit, Isaac Newton is the one that got the credit for that. But the idea now, see, for a function like this, you got the function f of x equals x squared, right? The interval I was talking about is the interval from 0 to 1. You guys see what I'm saying now? And so at least I know the function f of x equals x squared is continuous, right? Meaning we can just draw the curve without lifting the pencil inside of that interval. The interval here is intended to be the interval that we take the accumulation over. So at this point, I still stick with my explanation for you guys that a definite interval is an accumulation. Because you saw that through the Riemann sums idea and all that, right? So the interval would really is a accumulation idea. Okay? And so as long as your function is continuous inside of that interval where we are attempting to find a definite interval over, then so now the work I've showed you guys before, we got to go through the Riemann sum, right? Setting it up, and then f sum, the x, the left-hand points, right? Some I, and then multiply with the x, and then I from 1 to n, and then take the limits, right? We've got to set this up. And then doing all that crazy work just to get to a final answer of being a 1/3, remember? Okay? And so that was the work. They're very long and very tedious. But now with this work, it's telling us that we can bypass all of this. We can bypass all of this. Okay? The answer 1/3 is still 1/3. The answer will not change. It's just now we are legally allowed to bypass all of that work. But instead, what we do here is, you guys recall the capital F, and it has that explanation of what capital F is. Capital F is some function that's such that, hey, the derivative of that equals this function F. So what does that capital F have to be? The antiderivative. See what I'm saying? So Isaac Newton has proven that, hey, wait a minute, we don't have to go through the deadly Riemann sum, but instead you can just simply find the antiderivative. So think about it as a process. Antiderivative for this function, right, is that 1/3 x cubed. See what I'm saying? And plus c. Plus c. Sounds good? You guys start making some connection between the 1/3 and the 1/3 here? Yeah. So that's the antiderivative. That's the first step in the process. That's why it has this part here. Find the antiderivative first. And then this symbol is indicating the next step here after that is substitute the two upper bound and the lower bound of your interval into that antiderivative. So now the antiderivative here, I'm going to take the value 1, right? Subtract the antiderivative, because antiderivative in the end is being a function, right? An antiderivative is a function. So you can substitute x equals 1 into the antiderivative, and it's also substitute x equals 0 into the antiderivative and subtract out the two results here. So let's do some quick calculation. 1/3 times what I have here is a 1/3 times x. Oops. 1/3 times 1 cubed, right? Plus c, don't forget the c. Okay? For now, don't forget the c. Subtract, and then you got a 1/3 times 0 cubed plus c. You guys agree? That's just exactly how I substitute the antiderivative, right, into your work. And so for that reason right here, in that way, when we subtract it out, here you got the 1/3 times 0 over here, it's all 0 out, right? And let me write it out on my other board like that. So on this board, we have now 1/3, because 1 cubed is just 1. 1/3 plus c minus c. This minus c here comes from the other term. We have this earlier, 1/3 times 1 all cubed plus c, right? Minus, 1/3 times 0 cubed plus c. And so subtracting in, that's why we ended up with that minus c. So the minus c will cancel anyway as well. And your answer now comes out to be 1/3. Now you tell me the process we're doing now based on the Isaac Newton's work. We call it the so-called fundamental theorem of calculus, right? The second part. This process here, compared with the sum, the taking limits process, which one is faster? Definitely this one, right? It takes just, not even a minute to get it done. I got a lot of explanation putting in, but when you're actually doing the work. It's less than a minute. You know what I'm saying? That? Okay. And so now this theorem has become legal. And so the idea now is that when you're finding your antiderivative, look at the way how it worked out with you. In the end, having the constant c, when you're doing an antiderivative, having a plus c in your answer is a must, right? But now we're only using antiderivative as one step to get to the final answer of a accumulation of a definite integral. And so in the end, those constant c's here will cancel anyway. See what I'm saying now? And so now for that reason, now formally the way how we write the steps, just the same function. This is the way how we write the steps now. Okay, the integral of the function x squared dx. That's your function, right? And you know it's continuous. So earlier I was just explaining the reasoning for that and how it matches with the theorem. But now the way how we find it, the antiderivative is the first step, right? So what's the antiderivative? 1/3 x cubed. But here we use antiderivative, as I said earlier, we're only using the antiderivative as a part of the next step. And you can see in my thought process, in my working process, I've shown earlier the c will cancel out anyway. So that's why the antiderivative, this is the only case here that the antiderivative here, you can skip the plus c. See what I'm saying? Because it's going to cancel out anyway. So why wasting more time writing it? Okay. So anytime you find the antiderivative to eventually find your definite integral, right? Then yes, you can skip the c there at that time. This is c. So in your written work, it looks like that, right? The integral comes out to be first thing, right? Find the antiderivative, and then indicate that what's waiting after that is to evaluate. So this vertical symbol right here, we're going to evaluate the antiderivative currently found here by 0 and 1. Okay? But then we're going to make sure, see the number on top right here is the one to subtract. So we're going to have 1/3 times 1 cubed. That's the antiderivative at 1. Okay? And then we're subtracting 1/3 times 0 cubed, the antiderivative. We valued it 0 into that, right? So now your answer clearly comes out just being, once again, a 1/3. You know what I mean? Right? So this quick little part right here is the way of on standard anyone right, learning calculus is doing on standard. They're going to show an antiderivative step, how they found the antiderivative, right? And then we indicate that we're substituting values in the next step, right? So, and then in the next step, we're substituting values into that found antiderivative. See what I'm saying? Yeah? Okay. So that's how it's done. It took some more time for me to explain and refine that process. Right? In the end, we got the answers so quickly, and that's why it's called a fundamental theorem of calculus. Now, here's actually I lied a little bit about why it's called a fundamental theorem of calculus, actually. So let me bring that into the explanation here. You see, you guys are here for what people call count 2, right? And then the class you took before is called count 1. And in my teaching experience, in my experience working with calculus, the two classes that you guys are in, previously count 1 and now count 2, those are the two most important classes in calculus. Because traditionally, here's how it is. Traditionally, people call that differential calculus. And I believe I mentioned that a little bit. Differential calculus. This is where you learn about instantaneous rate of change in derivative and all that. Everything about derivative. And that was count 1. So count 1 is just for college. I mean, the college people call that count 1. But originally, it's differential derivative. Okay, differential calculus. You're doing everything about derivatives. And the purpose of that is rate of change. Remember that? Instantaneous rate of change. That's why it's differential. Sounds good? And then the kind of calculus 2 that you guys are doing, the kind of work you guys are doing, the count 2. It's called the integral calculus. You guys see why it's called integral calculus? It's all about we're accumulating. Everything I've been doing since the beginning there, yes, I spent a little bit of time doing antiderivative, but that's just a prepping work for you guys. Okay, that's just a prepping work. But then I put a stop on that. We just like after 1 day or so, we put a stop on that, right? And we turn over to Riemann sums and all that accumulating work. Accumulating work is the essential idea for integral. Integral means we're accumulating work, right? And so calculus 2 is all about doing all the accumulating work here. So accumulating work and finding rate of change is completely two different kind of work. In historically talking about the past, when mathematicians were making their search on for forming up this learning right here, then differential calculus and integral calculus permanently remain two separate branches of math. One kind of math is doing rate of change all day long, and the other kind of math is doing areas and accumulating work all day long. And the two kind of math has no connection at all. That's what I'm trying to point out. Until this theorem came out, it made that connection. You see, the finding area doing the accumulation work has a relationship with doing derivative work. By doing what? It's the reverse process of doing derivative work. Okay. See what I'm saying? Huh? And that's why it's called the fundamental theorem of calculus, because this theorem connects the two branches of calculus together. Okay. It points out a relationship. It's not any longer two separate maths that people got stuck with forever. See what I'm saying? Huh? And that's the idea. That's why it's called the fundamental theorem of calculus. And then starting at this point right here, it allows mathematicians and engineering and people doing any kind of advanced math work to start picking up the math work on the fly. Right? Because a lot of work out there, they do things as an integral problem, but they don't really realize it. And so Isaac Newton pointed out that, hey, if you do that integral work, all you do is find the antiderivative, which is the reverse process of derivative, okay? and then do the evaluation work. That's the formal understanding. Yeah?
What does count 3 cover?
So count 3 really is just the things beyond that. You guys mix between these work. At some point it's a differential work, at some point it's the integral work, and then we bring that into the three-dimensional space. See what I'm saying? And then count 4 you just go into further into the three-dimensional space, that's all. That's why like I said, the true fundamental understanding you guys start from here, right? Count 1 is the one, and then now count 2. You guys really learn the two major branches of calculus, and then count 3 and count 4 is just like how we keep applying that and push that into deeper applications. That's all. So that's some historical work on the historical the discussion about that. But let's now just do some examples. I mean, you've had enough tour here. Let's just start doing example immediately to enjoy that result that Isaac Newton brought for us, right? So let's now look at our first example here where I'm going to bring out a few. And so now you can see that the examples can go really fast. So it's just whatever example I'm bringing up here, it's just intended for you to get comfortable with the way how you carry out the steps, that's all. All right, so the first one to come. We want to evaluate. Part A, we have an interval from 2 to 5, right? And we got 3x squared minus 6x plus 2. Yeah. Right. Go ahead, take it. Write it down, and then at this point right here, if you feel so eager that you want to go ahead of me, that's fine, because you already know that's what it's legal now. Okay? So the first step, you get the antiderivative of this, right? And that's leading it to x cubed minus 3x squared plus 2x, right? And for this antiderivative here, it's only one step before the next more important step, right? That's why I'm just leaving that here as without the constant c. Okay? And then we go from 2 to 5. See what I'm saying now? So that's the first step of that, laying it down for ourselves. And then, so now when I start substituting it, so the only thing that I keep having my students mistaking all over is that they misplace the two values here. So remember the one on top here, that upper limit right here, you got to put it in first, right? So it's going to be 5 all cubed minus 3 times 5 squared plus 2 times 5. And that's the antiderivative evaluated at 5. And then we have, again, we got 2 all cubed minus 3 times 2 squared plus 2 times 2. All right. Guys, the final answer in these days, it's not important, okay? whether you understand how to get it right. Okay. So 16. Okay. So you've seen that problem. So let's look at another one. More opportunity for you to practice. Let me purposely bring you guys into a problem like this. Let's say I can go improvise a little bit. How about a negative 2 to 2 and a function here to 1. X cubed. Right? Just do a function like that. Should be easy. But anyway, so we gotta find the antiderivative, right? The antiderivative is giving me a 1/4 x to the 4th. You guys agree? And this time here we can skip the part C, right? Because we're preparing that for the next step. Minus 2 to 2. Okay. Easy enough to get yourself set into that routine of how we're getting the steps done with that. And then, so yes, now it's going to be a 1/4, right? And 2 to the 4th minus, right? And then now I'll have 1/4 times minus 2 to the 4th. Okay? Look good? Yes, it should be 0. Okay. We all good with that now? And so, I brought up this problem for a purpose right here. It's not just another problem to waste your time, because you really have had enough seeing of the problem of how you use the fundamental theorem of calculus. But I brought this thing up to clear out a couple of misunderstandings. That, of course, it's the way it is. Any instructor who start getting into teaching about a definite integral have to start out explaining it as an area. See what I'm saying? I brought up that problem that, hey, find the area under the curve between on the x square function, right? This is the x square function, and then the curve is, we got the area, I was explaining that as an area inside between the curve and the x-axis, right? Inside the interval. See what I'm saying? But then it's just a natural fault that as we explain like that, as the instructor is explaining it like that, some students are going to start misunderstanding that an integral is an area. See what I'm saying? Some students is going to start misunderstanding that an integral is an area, but as a matter of fact, it's not. Okay? An area is only an application of where we use an integral form. See what I'm saying? But an integral on its own is only a Riemann sum where you go. You see? A Riemann sum that you go to stripes with height times thickness. So some height, for example, the function right here, the x cubed function we got from minus 2 to 2. Minus 2 to 2. Some height stays below being negative. You guys saw what we with that? That's why accumulating those heights here, we got some negative area, and some positive area. And that's why they adding up together, they come up with a. So if you really want to think of an area, the final answer of an integral is a net area. See what I'm saying? It's more like a net area. Okay? And sometimes your final answer can be negative as well. Your final answer for an integral problem can be a negative. You can think about maybe in the picture it's give a portion of the graph that's completely below the x-axis. So it's not just area, because area needs to always be positive, but net area can be okay. Net area means some part stay below the x-axis, some other parts stay above, and then we can just net it out like a net balance in your checking account, something like that, right? And we may get a zero out completely. See what I'm saying? All right. And so make a note on that. So the answer, right, to an integral, to a definite integral problem, if you really love thinking of that as an area, it is only equal to the net area. It's not exactly the area. Okay? It's just the net area. Okay. Between curve, the x-axis, inside the interval from A to B. That's all it is. It's not the physical area. You want to say, yeah? Okay. So what about right. So let's find a definite interval. Something like this. Accumulation all the stripes, right, from 0 to pi here. The Joyce function is a sine of x function. Right? See, something like this. If we were attempting to use a Riemann sum here, then seriously, that was a good luck with that, right? Because after we substituted it into sample points and all that, is there a formula that Google can give us? No. Right? I mean, a lot of times, a lot of people believe in Google to what they call that Dr. Google, but there are still things that Google doesn't know. Okay? There are still things because not too many people know those stuff to put on Google. You see what I'm saying? No? So, well, gladly we got the fundamental theorem of calculus. The antiderivative for sine of x, right, is going to be minus cosine of x. Do you agree? Right. And then now we're going to evaluate that from 0 to 5. Right. And then that now gives me minus cosine of pi. Right. One group right here, that's capital F at pi, right? Minus, and I'm running out of space right here, so I'll write it in the bottom line will be minus cosine of 0. Good? Right. That's why now it's going to be what? This is going to be a minus, it's a positive 1, okay? Positive 1, and then that's making it a plus, and a plus 1 here, so your answer all together 2. That's good with me on that. Okay. And then depending on the picture. So for this picture right here, right, the sine of x function goes like this. You guys agree? Right? And then the 0 is here, and the pi is here. So this answer here does indeed equal to the actual area, right, in between that. But like I said, not always, right? So most generally, a definite integral is a net area. It's not simply just an area. It's only an area. It means it has to be a positive all the way. I'll do that. All right. And so now because of that, the essential idea in this fundamental theorem of calculus brought in the antiderivative as a process, right? And so for that reason, now as a notation, now we're legally saying it. You see, back then when I was teaching you guys about antiderivative, I was telling you, hey, you use this symbol only as an indication, right, to find the antiderivative, and that symbol will always come with the dx. But so back then, prior to getting into definite integral, we only see that as a symbol indicating finding antiderivative. But now it actually has a meaning. There's a reason why people decided to use that symbol right here. Because in a definite integral version, okay, after fundamental theorem of calculus came out, right, the big theorem here says that the big work is to find the antiderivative, right? And then substituting in, and that's why now we can kind of use that symbol for a reason that now we use the same symbol but without the two limits here, without the top and the bottom, and then on the same function, and still use the dx here. That now really, at this point, I'm talking about legally, okay, or officially, used as antiderivative. See what I'm saying now? Okay. Or and not only antiderivative, people now call that, see, it's the integral sign now. It's now the integral sign, but without the two limits, top and bottom, right? People refer to this as an antiderivative now is also known as, well, aka the indefinite. Indefinite. You guys see that? This version is called definite integral. You see that before? It's accumulation. But this version now, without the two bounds here, it's now called indefinite integral. Right? To be formal, it's just because we made that connection that anytime we find an indefinite integral, we got to go through the antiderivative step. So we now use that symbol, right? And we call that thing itself now the indefinite integral. It's the equivalent way of saying the antiderivative. Okay. Right. And so, indefinite integral, then making sense from what you've learned, it's got to come out being a function, right? Definite integral comes out being number or value. Numerical value, right? But indefinite integral is an antiderivative, so it has to come out with being a function. And when you are asked to find an antiderivative, right, or an indefinite integral, then you're going to have to add the plus c at the end. Okay? And that's the two major things we get. Sounds good? And so in that way, let's look into another example. All right, so in this example 2 over here, let's look at, we want to evaluate dx again. Okay, and you guys know immediately what I'm asking for, right? So this now, when you see this symbol, yes, formally we call that it's an indefinite integral, right? But really, it's nothing but just the antiderivative. So now we just go ahead and find the antiderivative. 2 times e to the x, right? Because we keep the coefficient 2 itself, right? And then e to the x repeats plus c. That's the answer. See how simple it is? Okay. And then quickly, there's another brief one right here. Let's find the indefinite integral. Or for short, people call it the integral of 2 plus x times x minus 3 dx again. Okay? So, yes, that means we are instructed to find the area, the antiderivative. But now, more formally, we call it, it's the indefinite integral. But really, we didn't learn any fancy technique, and what's worse is that we don't have the product rule, and I mentioned this earlier, right? So the only way of getting this, we FOIL out, right? Okay, a little too much. FOIL it out, like that, right? So this is now, I'm talking about the algebra work before the actual antiderivative work, before the actual calculus work here. So we got 2x, right? Minus 6, right? Plus x squared minus 3x. That there, dx. So we can clean up the terms. So one more step, I'll be rewriting the antiderivative symbol, the indefinite integral symbol. So we have x squared, right? And that's minus x minus 6. Guys agree? Right? So now our final antiderivative is ready. Our final indefinite integral is ready. 1/3 x cubed minus half x squared minus 6x plus c. That's what we got. Okay. So let's look at an example here. We don't know what that function is. We just don't. Is that an x squared function? Is that a 5x cubed minus 3? Whatever. I don't know. It's just some function f of x. And the integral from minus 3 to 3 is given to be 9, okay, something like that. Right. And then we have another function, another integral. So we got two integrals given here. How about -1 to 3, same function. It's given to be like 10.7, something like that. Okay. So those are the two given known integral values. Let's find out, let's calculate, right? Or evaluate, that's a better name, it's a better way of saying it. Evaluate the integral from -3 to -1. This function f of x dx. Okay. So that's the intention of the problem. Along this way, we have done about 2 examples, so we can call this example 3 for this lecture. Okay. All right. Are we good to get into that? So with this problem right here, the first thing to notice now. We don't know the functions, right? But we're given 2 integral values, and we're actually finding the third one. So, since we don't know the functions themselves right here, the best way is to tackle down and say focus on these integral intervals, right? Integration intervals. So the longest one, because when you draw the picture, right? So -3 to 3, whatever the function is, right? But the integration over I mean the integration interval is from -3 to 3. This one here is from -1 to 3. See what I'm saying? No, that means the -1 clearly is somewhere in between, right? So that's why we're using that other theorem that I brought up earlier. If C is some value, inside of an interval from A to B, right? Okay, so relative to this property that I pointed out right there, then I'm seeing this 1. I mean this -1 here as a C. -1 is being inside of the interval from -3 to 3. See what I'm saying now? That's just some, and you don't even have to indicate that. It's just something that we observe and we notice that. Okay? But after realizing that, after this realization, then once you clear with that, then here's one thing definitely it has to happen. According to the properties, right? The total integral from -3 to 3, that from that longest integral, that longest interval, the integral over that has to be, or has to always be equal to the integral from -3 to -1. Right? We're breaking it up for here into 2 separate accumulations, and then another separate integral from -1 to +3. X. Yeah. You guys follow what I'm doing right there? So that comes straight out of the property, right? Once we have realized that the value, one of the values falls inside of the total interval. And so now we start putting in the known information. The total interval from -3 to 3 right here. The integral on that is a +9, right? It stays on the left-hand side of the equation. So we're looking at 9 equals, right? The integral from -1 to 3. It's this guy right here. You guys with me on that? That's a plus 10.7. Right? And that's it. It's given. So the unknown one we're looking for, -3 to -1. The integral from -3 to -1 for that. It's right there. You guys good with that so far? Right? And so now we're ready to find that final answer. What can we do? Subtract 10.7 from both sides, right? That's a simple solving the equation problem right there. 10.7 on both sides. You want to say no? Right. So it's the answer here. After doing that, right? Allow me to swing back on this board right here. What's the final calculation for this? See? 9 minus 10.7, right? Which is a negative of 1.7 here. That's the final answer. I'm picking it up from the other staff. All right. And so if any of you is having some curiosity in mind and some concern or some worry in mind, wait a minute, how can an integral be negative? Okay. Or if you're looking right here, because I taught the exact same class somewhere else, and when I brought this up, forget, right? In an earlier lecture, at other place, then a student's already concerned that, hey, how come this this part right here, right, is bigger than the total sum? See what I'm saying? No? But that's completely okay, because think about it. The function could be like this: some negative part and some positive part. See what I'm saying? No? Okay. And so, because I did use admittedly, I have to admit that it's the way how it is. Anytime we start teaching about an integral, we've got to bring up area as a way to visualize an integral. But I keep telling you guys, and I've been telling you guys that, right? An integral is not always an area, okay? Because in case the function can sink below the x-axis like that. So this part right here is some negative portion of the graph. So an integral, from what we understand, what I explained yesterday, an integral really is a net area. Okay? So an integral from A to B. If you really want to think of that as an area, it truly is the net area. Meaning, think about the curve right here. Some part of the curve stays above the x-axis. Some other part, some other interval, it stays below the x-axis. See what I'm saying? No? So who knows? For this problem right here, that portion from -1 to 3, yes, it was a 10.7. Okay, but then because the portion down here, there's some area saying -1.7 being below the x-axis, right? Accumulated out to be a -1.7. So the total accumulated net area came out a +9 only. See what I'm saying? No? Right, and that's the idea again. Right? Yeah.
Question. So let's say we have an integral from A to B, right?
From where to where?
From A to B.
Okay.
So it's integral from A to B, and it's fx times g of x dx.
Okay.
How can you express that integral with f of x and g of x?
That will have to come later. Actually,
Okay.
we don't have a direct rule for taking the integral on the product of two functions.
Okay.
So right now we only have a rule for taking the integral on the sum or the difference of two functions. Okay. All right. And so, any question on this particular problem? Okay. So that's pretty straightforward for that, right? Okay. And so now, after this point right here, we start taking that into even further. We're expanding our understanding even further. Now let me bring up a problem like this. Example 4. At this point right here, I've already introduced a fundamental theorem of calculus, right? And we've learned that nice way of solving it, right? And I've been making it clear that the integral itself is not necessarily an area, right? Because some part inside of that integral could sink below the x-axis. So the most precise way of thinking of an integral is to be a net area. See what I'm saying? So watch out for the wording for that. And so I'm going to produce a problem as follows. Let f of x, right, be, how about x squared either side of the interval from -3, 3. Thank you. And so for this problem right here, we definitely need to have the picture and pay attention to the wording. It's asking for the net area, right? It's asking for the net area. That means simply you got the interval right here, and the net area between the x-axis and the function, between the function and the net and the x area and the x-axis inside that interval. So that area just basically means the interval, that brutal interval from -3 to 3, right, of the function x squared minus 4. See what I mean? So the net area truly is just the interval in how we have already understood it. That. So net area, that equals this. So what's the picture of this looks like? The x squared minus 4 is -2 here, 2 here. The x squared minus 4, I'm off scale a little bit, kind of like that. See what I'm saying, huh? Okay. And so the bottom peak right here is a -4. Like that. But now the point here is that we're integrating from -3. -3, 3 with that. That's why in this picture, that's why I'm calling that as a net area. Because the total integral here goes like this. Some part of the graph, right, stays above the x-axis. You guys follow with me on that? Some part of the graph stays below the x-axis. Some other part swinging back to be positive. That's why the total accumulation as an integral, the total accumulation all the way from -3 to 3, it contains all of those negative, positive, right? And that's why in the end we call it as a net area. But truly, a net area is just that total integral. Down to that. And so now feel free to use that nice fundamental theorem of calculus that you've learned right there. What you do for this? Find the antiderivative, right? 1/3 x cubed, and you've seen all of those two right there. So now the next term, right, we find the antiderivative term by term right there. So -4 for x. We can skip the plus c here because the antiderivative we're using here is only one step, right? That's for that's only one part of the step to find the final answer. And now -3, 3. Okay. And then the final answer here is going to come out. We're going to substitute these the limits into a function. So 1/3 times 3 cubed minus 4 times 3. That's the antiderivative evaluated at 3. And then we're going to produce 1/3 times a -3, right? All cubed minus 4 times -3. Okay. It's a trap. So now you guys can go ahead and help me out with that calculation of that. Keep the final answer in the fraction for you. All right. So I've been waiting hopefully long enough. So any final answer? Yeah?
-6.
-6. Anyone would like to confirm? So, for an integral, it's entirely fine, right, to have a negative answer. So what I'm saying, because as we knew, it's just the net area. So who knows, some negative part of the graph, right, some positive part of the graph. So scoring out, making a net balance, right, of all of these the areas, if they're negative, positive, it could turn out to be a negative answer. Completely fine. So the wording here is it's asking for net area. All you do is just get straight into the finding the actual interval, right? Inside of that designated interval, you should be good. Okay. But now I want to erase this out. I still want to keep the graph here because it's the same function. But for part B of the example, be careful with the wording. That's it. Okay. We want to find the area between the function and the x-axis inside of that interval. All right. Ready for going in? The question here is actually asking for the area, no longer the net area. So now you have to understand here it's talking about some actual geometric area, meaning all areas are going to be positive. See what I'm saying? That when you're actually being asked to find an area, now you're going to have to think about the real meaning of an area. Even though this part here stays below the x-axis, you're going to have to find some way to calculate the positive amount out of that. See what I'm saying? Because the actual physical area, okay, got to be positive. See what I'm saying? No? And so in that way, here's how, so with your graph here being broken up into three separate intervals, three separate areas, right? Some area stays above the x-axis, some other area physically sits below the x-axis, and some other area stays above again. That's why now when you're calculating as an area, here's some trouble that we have to go through right here. The area, now we're going to have to do some breaking up here. It's -3 to -2 right here. And it goes just simply x squared minus 4. You guys following? Because x squared minus 4 in this interval from -3 to -2 is entirely positive, right? That's why we stay with the same function itself again. Then that's not the whole area of this graph, right? We got another portion, so we're going to need to add. But then from between -2 to 2 right here, the function x squared minus 4 is indeed below the x-axis, right? So if we're doing this brutally right here, if we're just brutally doing this, we're going to come up with a negative result. You guys see what I'm saying? No? Okay? I mean, take a pause again. Do a quick math on that. Just that one. You guys go ahead and do the math just on that interval. X squared minus 4, right? From -2 to 2. Tell me if you get a negative or positive answer. It's a negative answer, right? Because it explains that because the graph here stays below the x-axis physically. But now the point now is that we don't want negative answer. See what I'm saying? We don't want negative answer. The picture is telling the story already before we get into the problem. So to fix that problem, like I said, we want area, but area, none of the area is supposed to be negative. That's why for any area, any part of the graph that stays below the x-axis, we gotta put negative sign there. Because the negative sign is going to do the trick. If we're going to flip that particular part upside down, see what I'm saying? No? So think about there's a magical switch like this. See that there? Okay, and then we calculate this area on top. That's the idea of that. Okay. So instead of just the brutal integral from -2 to 2, right? We do the integral from -2 to 2, but of the negative, right? The opposite sign of your function right there. That's the idea. So that will definitely produce a positive area. So in the end, this part right here will be that answer of yours, but the opposite sign. Okay? So you got the middle area, and the third piece right here, see the graph is telling you the story. The third piece is already above the x-axis. So we're going to add. But this time, do we need to flip the sign? Nope. 2 to 3, right? The function stays the same, x squared minus 4. Yeah. You guys doing that so far? So at this point right here, yes, now we're ready for some final calculation.
2.333 repeating.
Okay, 2.333 repeating, so that's making it 2 plus 1/3, right? So which is a 7/3, right? That one here is a 7/3. You guys agree? Okay. What was the middle one that you had earlier as your negative answer?
It was a negative 10.6666.
Okay. 666. Good. Negative 10.666. Right. So it's going to be a 10. Yeah. Positive 10.666. Yeah. But 66 is a two-thirds. Okay. So it's going to be a 62 thirds. Yeah. If I do my math correct. And then the last one here, I don't think you need to do the calculation because the picture, I mean, you can do the calculation as well. You're highly recommended, but I can tell the picture is exactly symmetrical, right? So I can tell that the answer will be another 7/3 right here. You guys follow me on that? Yeah? So now as far as area, now we're ready for summing up the area. The total area is making it the final area here. Final area 7/3. 62 thirds plus 7 3. So that's going to get 14, right, with the 62. That's going to make it 74, 76, 43. Right. That's the final answer. Be a positive